I'm Ayush, and this is our second video in binary search playlist. And in this video, we'll be discussing about inbuilt functions for binary search in our C++ STL library. If you have if you do not have any idea about binary search and want to know how it works, all the basics about it, you can watch the previous video in this playlist. I'll just link it down in the description. But without further delay, we'll discuss about two most important functions in our STL library, which are used a lot in our binary search implementation. And like to write simple binary search, it takes time. So we like save our time by using this STL functions, like in many of the cases. So these are the two functions we'll be talking about in this video. So first is our lower bound function, and second is our upper bound function. We will discuss how are these functions, how can we use these functions, what do these functions do, what arguments do they take. We will discuss simply by examples. We can I'll tell you what these functions are, what it does, and we will discuss like 3 to 4 examples regarding this function, and like where can we apply this function and all. So let's get into it. So for low bound, focus here. So for low bound, this function returns an iterator or pointer of an element which is equal to or just greater than target. If I have a target element and like I use this low bound function to find this target element, I will get an element which is like equal to target. I'll get the element directly equal to target. I'll get an iterator or pointer of that element which is equal to target. Or if it does not exist, if target does not exist, I'll get an iterator for that element which is greater than target. Got it? And for upper bound, uh, this returns an iterator or pointer in case of arrays of an element which is like strictly greater than target. Okay? If the target exists or does not exist, this function would return me an iterator which is like strictly greater than target. We will like clear this through examples, so not to worry about it. But like before that, we will get into basics of iterator. What iterator is basically, you can say, a pointer itself. Pointer is wrapped in a class with some functions, inbuilt functions. Iterators are just used to traverse STL containers like vectors, sets, maps, etc. So yeah, and in case of array, this function in case of array, with this function return a pointer, and in case of vector, set, multiset, or map, these functions return an iterator. So I told you what iterator is. So now in a simple vector, this like the first zeroth element, this is our zeroth element, and this is 0 1 2 3 4 5 6, right? So the v dot begin or first iterator returns, basically denotes the zeroth element of our array, right? Not the index, it is an iterator, so it is similar to pointer. What it would store internally is an address, so this is where it points to. Okay, and v dot n, v is the name of vector, and v dot n would not denote the last element of the vector, but instead it would denote just one address after the last element. It is an integer array, right? So this address can be, let's say, 1008. So it would denote, if it is an integer array, we can just do 4 bytes. This would give 1012. This is denoted by v dot n. So it would denote one position after the last element. So these are just two iterators you should know. And in case of vectors, you can do uh, pointer arithmetic with iterators as well. I'll explain that in code. So just for now, just focus on like understanding this lower bound and upper bound function. We'll get into iterators later. So let's get into example really quick. So I have this array, right? So also, as this upper lower bound, also one more important thing, this like lower bound and upper bound function, as they implement binary search internally, so they have a complexity of, yes, you guessed it right, they have a complexity of log of n, where n is the size of array, so O of n. And for this function to be like used correctly, we need our array or any container, vector, set, anything, to be sorted. So we can only use this function if our any container any data structure is sorted. So yeah, let's get into example. So we have target equal to 40 in this sorted array of 10, 20, 30, 40, 50. So as I said, lower bound, I'll pass this to lower, I'll pass this array and this target to my lower bound function and upper bound function. So lower bound would return me an element ka iterator which is like less than greater than or equal to 40. Now as we can see, 40 does exist in array, so it would internally implement binary search, and we will like have an iterator of 40 here as 40 exists in array. And upper bound would return me iterator of 50, as it would like strictly give me iterator greater than greater than target. Like target is 40 here, I'll receive an iterator from upper bound function which is like strictly greater than the target, which is I'll receive 50 here, right? So now let's take another case. So in this case, I have like my target equal to 42 and we have same array. Okay. So in this case, like if my target is 42, I can see that my target does not exist in array. So my lower bound function, what does lower bound return? It returns element iterator which is greater than, which is equal to or greater than target. So it does not like 42 does not exist in our array. So we will return an iterator which is greater than or 42, which is 50 here. And similarly, like upper bound returns just greater than target iterator. So it would be 50 again. That's it. So let's take another example as well. Let's say our target was 53. It does not exist in array. So now what? So the largest element in this vector or array is 50 and we want something 53. Array is sorted. So if it does not exist in array, we would like get here v dot end actually, right? The lower bound and upper bound both would both functions would return an iterator which points to end of our vector. So yeah, like if it does not exist, if like this element does not exist, right? So uh if our like in this case 53 is greater than largest element as well, then I would return something hypothetically speaking v dot end. This is hypothetically speaking greater than all elements in array, right? So I would return like the end wala iterator here if it does not exist. And in this case, like if our target is 8, we have the same array 10, 20, 30, 40, 50. Like the 8 also does not exist, then what we would get? In this case, like I would get 8 does not exist, so lower bound is not able to find it, but it would return me something greater than 8. So something great, just greater than 8 is 10. So lower bound would return 10, and upper bound similarly would strictly return something just greater than 8, which would also return 10. So yeah, that's it. And uh like this is how the lower bound and upper bound functions work. How do they like what do they return and all. Let's get into code and actually see things how we can code them and what arguments do they take and how do we implement these functions. So let's get into the code. So let's try to implement our lower bound and upper bound functions in array. So let's start with, well, implement like I'll show just implementation of lower bound. Upper bound is similar, but yeah. uh let's have an array of size like the same array we declared. Let's have it 10, 20, 30, 40 and 50. Now what I said was like lower bound function would return an pointer in case of array. So I would have an int pointer, let's call it lb. It would lower bound function would return a pointer. So this is a low bound function. What argument would it take? It would take arguments of search space. So the first argument of low bound function is start of search space, and second argument is end of search space, and third argument is our target. So in this case, like I'll just write it down. So low bound function would take start ptr, like start of search space something, start of search space ptr or iterator, right? Second argument would be end of search space plus 1, right? I'll pass into arguments list plus 1 of end of search space. Like if my array is of size 5, the search space is from 0 to 4, right? Index 0 to 4. So end of search space is just 4 plus 1, 5. I'll pass it 5 instead of 4. The code will make it more clear. So just write it down so that you can refer it, and we'll have target. So this is how our function argument would look. I've like written it very long, but yeah. So the start of search space will provide the starting pointer of our array, which is stored in array itself, and we would have a size of array. In this case we have size 5, so we would have end of search space arr plus n. So this would denote end of our search space, end of our search space plus 1 to be precise, right? So and our target, let's say I have to find element 20, right? So this would give me low bound. This would find me element 20 if it exists. If it does not, like it does not exist, I'll find something greater than 20. Similarly, we can write upper bound ub equal to upper bound of array plus n. Similarly, we have like same arguments. This is the start of search space, this is the end of search space plus 1. And if you don't know about what is search space, just check out my previous video, and like we will pass in 20 as well. Let's try to print a low bound and upper bound. Yeah, let's try to print it. So you can see the output here. For low bound output we have 20, and for upper bound output we have 30, as we have discussed, so it is fine, I guess. And like to get the index, like this is an pointer, right? LB is a pointer, I'm using star to dereference it. So to get the index of low bound, what I can do is, low bound is a pointer, right? And I can just subtract the base address of an array to now get the index. Just to just print the index. So yeah, index is 1, the low bound value is 20. This low bound is pointing to this 20 here, so this belongs to index 1, 0, 1. I'll get this just by pointer arithmetic. You should be aware of pointer arithmetic. So this lower bound pointer minus the array ka base address would give you index, right? So yeah, you can similarly do this for upper bound as well. You can just do up minus arr, and you can check the output here. This is index 2, so upper bound is like 30, which is at index 2. That's it. So this is for case of array. Like now let's discuss in case of vector. Let's actually copy this our array so that we don't have to write it again. So in case of vector, let's declare a vector of int b equals to this, right? And let's write upper bound function, like so low bound function as well. So what I told was it returns an iterator. So uh, so low bound function is something like this: lower bound v dot begin, v dot end. This is start of our search space, and v dot end is my end of our search space. As like let me just show you again. So like as I've told in our example, this is our beginning, this iterator shows the beginning, and this is the end, which is just after the last element. So this position and this position are given as arguments. So let's come back to our code. Yeah, so back to our code, I'll just pass this two arguments and the target. So let's write target here as well. So and target equals to, we'll take the same example, like we can take 30 here, right? So I'll just pass in target as my third argument as well. So now this returns an iterator. I need to store that iterator in order to use it. So I can, so as it returns an iterator, I have to write, let's call the iterator lb equals to low bound, and this is of data type vector of int iterator. Spelling of iterator, yeah, am I right? Yep, it's fine. So this returns an iterator. Now iterator is same as pointer, you don't have to worry about it. You can do similar operation, you can just dereference it. Let's value, let's call it, sorry, value, value of low bound is, just dereference the iterator. And for index, what I can do now is like, let's write it index of lower. For index, you have the low bound returns an iterator. So let's say you have this, so low bound returns an iterator. Let's say like we have the element 30 now, right? So uh this is returned by low bound. So this is also a pointer, you can just do pointer arithmetic, subtract low bound minus v dot begin, you'll get the index of this, right? So let's switch scenes again. You can just do pointer arithmetic again, lb like the iterator minus or v dot begin would give you the index. You can verify it by just printing. So yeah, the value of our low bound is 30 as expected. It has found the target as it exists in our array, and index of our low bound is 2. It is correct. This is 0, this is 1, and this is 2, right? So this is correct. And if what if we are change our target to 34, let's say it does not exist, right? So now our value of low bound is 40, which is like just greater than 34, right? So it returns 40, and index at which it has found 40 is at index 3. This works fine. This is just pointer arithmetic. And next, like other example as well, if like we give it 55, it does not exist in array, then what? Then I'll pass it. Yep, the value of low bound is 0. Okay, so you cannot dereference it, as this iterator is now v dot end lb when the element does not exist in our array and it is greater, like the it is 55, target is 55, right? So the iterator stored in lb is now v dot end. So in this case, uh lb is equal to v dot end, and now this iterator, this cannot be dereferenced, so you cannot access value from it. This is printing 0, but this is invalid, so you should not actually do this. So you can actually always check if lb is not equal to v dot end, then only we can write this c out, else we can just write out of bounds, and lower bound of the target does not exist, right? So this is a simple if else. Yep, and just write enter tax space as well. So as we can see, this is now out of bounds, and lower bound of the array does not exist. We have printed this, like obviously, and index of low bound will still get an index, valid index, because this is not valid index, but this is how we denote, like the arrays of size varied. The last index is last index is 4, you'll get index 5, which means like you are at the end of array and it does not exist. Yeah, so as simple as that. Now like you don't have to write this complete again and again, vector of int iterator, this is like very long to write. What you can do, just use an auto keyword, so this would automatically configure what is data type of this based on the function. So you can now, like this is the same now, this was vector, right? You can do similarly for set. Now set, the function, like the implementation changes a bit, like the low bound function is included in library algorithms, but set has some different implementation. Instead of like writing the function like this, the set has inbuilt method for it. Let's call our set v, right? Let's call our set st, sorry, and this is like, we can just do some st here instead of v, and now low bound equals to st dot low bound, and instead of like passing our search space, now search space now becomes the entire set or entire map or entire multiset. You can use it for anything. I'll give an example of, you can do with map as well. So now this function now takes this argument of target, right? And this should be fine. And you cannot, another important thing, let's comment this out, I'll explain it later. Now target is, let's say, 30, right? So we'll be able to find target now. Yes, the value of low bound is 30. Yeah. uh so set has inbuilt function for, and set is a class, right? Set of int is a class. So this set object has inbuilt method for low bound function, so we can implement it directly. uh, about this pointer arithmetic, the set is like implemented in a red black tree internal implementation. So the addresses are not contiguous, so you cannot do pointer arithmetic here. In vector and arrays, the array elements are stored in a contiguous order, but in set it's not. So like there are random addresses, you cannot just subtract address to get the index. For this you need to like use ordered set, which is like beyond scope of this video. But just to remember, you cannot do this pointer arithmetic in case of set. This is invalid, so you cannot do it this in case of set, map, or any thing which implements a tree in its backend. Yeah. uh Another thing is like, for you can do this for map as well. So map has a similar syntax. We can do map of end comma int. Let's have our elements. It stores a key value pair, right? So we have key as 10. Let's have our value as our index itself. Let's say we can have 20 comma 1, and let's have 30 comma 2. So it's a map of, yeah, now that's fine. So in this case, now our low bound function auto lb would be map dot low bound on, let's say, target is my 20, right? So in this case, the 20 is my key, and I'll apply this lower bound function on keys itself. I'll not apply this function on values. I'll search through keys. I'll apply binary search on keys, and I'll find the value 20. And now lower bound index like returns an iterator to the key value pair, this 20 comma 1. So I can just access it using lb. This is to dereference it. We have like, this is an iterator, right? To dereference it, either I can use star operator, and then I can do first, or I can just use an arrow operator, something like this. You can read about arrow operators and star operator. These are like basic things about dereference and reference. And this is lb dot first, and this is lb dot the arrow second. So we would get the output. Yep, we got the key as 20, and this is value as 1. Yeah, that's it. I think we cover it now. Just one thing you need to keep in mind is like the low bound or upper bound and map, just like this function applies on the key, not values, so just keep that in mind. Yeah, I think we have covered everything now. Yep, we have covered everything. So that's it from my end, and bye bye.